Perché mi ha trovato utile. Io ho trovato questa roba. Ti risulta? Quindi questa che prende in considerazione. No.
Era per i rifiuti quella.
Io ho capito che c'era una cosa più generale, evidentemente no. Che l'unica che ho trovato.
Also, some people visiting us, right, on Finland.
Yeah, exactly. What do you
Anyway, now I would say that, of course, we should have some time to present each other. Let me just manage this part, just to present myself first of all, so to break the ice and open the discussion on this course. And then, of course, we will have some time to play around with you. Maybe not in the real beginning, but just later in some moment of this first day. Okay. So first of all, let me introduce myself. I'm Marco Macchi, and I'm one of the teachers of this course. Basically, I'm the coordinator of the course. Also, probably some of you knows that I'm involved in the role in the PhD program. I'm vice coordinator of this program, and more than that, let me say, I would say that my origin in terms of area is industrial engineering. We look at my background, which is important because in the end, what I'm going to transfer to you is based on my background. I cannot say the that from my background. So what? Just let me go in the output. So it's a pleasure to be here, of course. It's not my first time doing this course. I think it's a long time, so somehow I was experiencing some improvement. Also, the course has been changing the time because of some methods. First, let me say personal method, more experience you have, more ideas you can bring to the course. Second, was what I think that in the last year, kind of transitional ages, which means that probably I bring some challenge in this regard during the course, considering the current years we are living. So I was teaching this course since my very beginning. I don't remember, but it is like 2 decades or less. It was named Modeling, and probably it was not exactly the same name as today. Don't remember in detail, but it was like modeling and simulation, or modeling and analysis of complex systems. And to tell a little bit about myself, I come from the industrial engineering area. I'm very much involved in let's say, factories, so manufacturing. Indeed, I'm represented in the group that deals a lot with manufacturing issues. I have some experience in some part of the group in infrastructures, because one of the specific disciplines I'm dealing with in my activity, with my research, is maintenance and asset management. which means that, of course, complex systems such as infrastructures may be of interest. So this is a particular focus I have in my experience. The experience I have majorly is with railway infrastructure. So, of course, it's large scale. It's on the country level side. But we're dealing also with some smaller scale, still larger, because it's regional scale. We're working in infrastructures for gas distribution, electric distribution, and so on. So this is just one part of the discipline that is in my background. But in general, the core, my group, I represent the group I'm part of, is manufacturing. And in that sense, I would say that I would like to remark that I have also some role in international journal, for example, associate editor of Journal of Intelligent Manufacturing. So this relates to AI, or intelligence in general, intelligent methods to make better manufacturing. And probably this is also part of my background in the sense of, maybe not in a direct sense, but some examples may be influenced also by my role as journal intelligence. This is just to present a little bit of myself. I would try to move a little bit out of your presentation just after some breakouts and some moment where we're stopping a little bit the discussion, and so we will make a round. Can you hear me in a good way from the remote connection?
That's okay.
Okay, so good. So basically, you know that this course is not only held by myself. You will meet Lisa Negri and Andrea Moro for specific lectures in the next days. Today is the first lecture. Today I'm breaking the ice. Today will be the most difficult lecture because it's the most conceptual. In the sense that we will deal with concepts, with some principles behind the course, rather than techniques or methods, which is important in the end to have an imprinting to the course. So I will record my presentation, so this could be available to you, also to the people that are not inside this university. You could reach also this link, we will provide you. You may know that some persons are participating as external person with respect to the university, so this means that, of course, we have some limits. Of course, the physical sense is a limit. They are mostly on the remote connection. I don't think that people from outside, except you, are here in presence. So I will start registration if you agree. Basically, of course, we may have some exchange, especially today it's more, let's say, an imprinting, and so a background that I'm providing to you. Also, we'll introduce you to some organizational issues of the course, like the assessment, but I will move it to the end of the day. So we'll start now right in the middle of the concepts. I was thinking in the last year how to start this course. No? So to give a general idea in a few senses, in a few elements, but for the whole course. And it was difficult to be, let's say, somehow synthetic in the message I want to give you, at the same time effective. So I decided not to talk about the topic of the course, but to start from examples. So this is a forward of the course. You see this picture, no? This picture is taken from the desk of one, I would say, organized person. It seems apparently very disorganized. It's a messy situation. But I'm close to him because I'm more or less in the same situation. But I understand one method. Probably we can share it. If in this apparent disorder, if there is a logic, you know the logic. You find it very ordered. No? And this is course, is a promotion of my attitude to create this disorder, apparently, but also to give you a first general message. Any kind of system you look at, even if it appears with some disorder, it is a matter of a logic behind it. So you have a logic to understand behind that system. And this logic, of course, if you think about this case, a specific case, if you see from the point of view of the photo, you see a lot of disparate piles of documents. It seems very complex, the organization of these documents. Apparently, you have the feeling of a disorder, but if you discuss with the person there on the desk, he has some logic in these parts. So the matter is that any kind of system that appears to be complex has a logic here. Then probably this logic is not fully expressed, is in the mental models of the person there, and I think is a very well-known person, Igor. So probably I can rely on him based at least on his career. But this seems that you may have some logic, which is in the mental models that this person has to organize things in this file. Okay? So this is the first message. Of course, this is just the first example to start from. The logic behind the system is important to manage the complexity. Okay? Second, of course, this is not a personal system, it's a technological system. You have the photo of the cockpit of an airplane. In this, of course, you have a crew that is working there, and of course, this crew should be prepared to work during the flight. It's obvious because we want to have a safe flight. And if you see this technological system, the whole picture, I mean, without details, of course, you assume this as a complex system. You have a lot of hardware, software things that are there, combined together to have some kind of organization of elements that are useful during the flight for people from start to the end, okay, for the crews, for the pilots. Also here, of course, it's a complex system. Also here, you will say that there is a logic behind that. I would say also that here, of course, you cannot rely on your mental models of people. You have to document in specific formal models the logic of the system. Because in the end, you have a lot of follow-ups. Think about the training and so practicing the skill of these pilots before flying. Think about only this element. It's clear that before entering this kind of instrumentations in the current use, you need to practice this and practice your skill. So you cannot start from mental models, which are, of course, in the mind of some persons. We have to formalize them. So to have the logic clear, like in an open box. Okay? So for this reason, it's clear that it's not only a matter of logic, it's a matter of modeling this logic informally. And so this is another message that is important for the course in general. Besides that, this logic, this is written as underlying extractor, let me say. This logic is the result of a design activity. When you are having this system available, this is a result of a lot of design issues that were solved before. So this is another method that relates to the course. I'm focusing from the point of view of the design of new things rather than observation of existing things. Okay? This is an important element that gives you the very basic essence of this course. I would use design activity, I would use engineering activities, I could use engineering design. I would talk about research of the engineering design. In that sense, I feel that I'm an engineer that is creating some new system, new algorithms, new models, whatever. as you like. This is the major goal I have in mind: creating a new system, new algorithms. That's the mindset I have for the whole course. And of course, to create these new things, you try to express some logic, for sure. It's not enough. You have to evaluate if the logic works well or not. That's another method. It could work, not, could have some pitfalls, and this tells you about another relevant method. When we are designing, we are having iterations. We are having trial and errors. This is the normal life of design. Intended as engineering. Engineering things that have some technical issues to be solved at the end to have the real system. Okay? Again, any kind of system, this is valid in general. When we will make a kind of round between us, you will tell me, I will ask you to tell me the topic of your research, your origin in terms of discipline, where you come from, you're a mechanical engineer, you're something else, you say mechanical engineering just randomly. But just to say that here we're not having only management around. Okay? So I like this as a start. I hope this was enough for you to give you the main messages of it. This is enough. Then, of course, we are entering into details. You are a designer. You have to express the logic. You have to try, make some errors to verify the logic and improve the logic. That's the overall sense of it. Okay? So that's the main point I would like to bring into this course. And of course, I told you, it's the most difficult lecture today because it's really concept. But if you can follow me, the way I will do will be relying on some theories, but even to some extent on cases. So to map the case with theory, and I would invite you to think about your own cases, because this will be essential not today, but for the whole course. Okay? Is that okay? Can you follow me?
Yes. Yes.
On the remote connection, is that clear? Can you follow me?
Yes. Yes.
My voice is good, not so bad after Sunday. Is the fact of there is a discontinuity between the weekend and the beginning of the week. So maybe there are some. So basically, my first lecture is organized in 4 topics. The last bullet point is related to some examples. The 4 topics will make more precise consideration of what is a complex system. And I could relate this to system thinking, which is essential, but at least in the mindset. Some of the technique that you will see relate to system thinking, but it's a matter of mindset. Okay? When you are in front of complex system, you should be able to think about the whole connections of different elements in the system, which makes a messy situation. But you have to deal with this. Okay? Because otherwise, for some reasons, you're not able to capture some objective or some interest that are around this. Okay? So be, in a large sense, a system to deal with the complex. Second, I will discuss about, as I told you, research of engineering design. So I will give you a short insight on the design science research, which was, let's say, introduced as a formalization not so many years ago. But if you think about the roots of the design, let me say, I would say, it's in the history. Leonardo da Vinci. Design things to solve problems. Design some elements to solve problems. That is the very essence of design science research. That has been introduced as a kind of research methodology, as a kind of research paradigm somehow. And I'm saying paradigm just to think that there are some differences with respect to some other research paradigms that are typically present. So in this second bullet point, I will discuss a little bit about what is design science research compared to other kind of paradigms. But also, I will give you a first concrete element that could be helpful for you. I will talk about a nominal process of design science research, like a number of steps to go through. You may have different patterns to go through, but you may have a reference model to think on the way to go through the design science research. So in that sense, I'm giving you the first complete element of it, besides the third, I'm back to the system thinking, but I will see in terms of models of the system. Virtualization is an important part in general sense of the course. Models can be of different kinds. So there you may see more, let's say, overall use of the virtual models of the system within a learning cycle, which is also a decision-making cycle. So in that sense, we will be based on the use of models to enable some decision support, but also some learning process. So to enable some good, let's say, result for the complex system. Okay? So in that sense, you understand that models are essential to make a good result in the end of the research. Okay? But I will be back later on this because it's too high level. Of course, I will make some kind of classification of the models, which is useful for the next lectures, because in the next lecture, we're going into more details into these categories of models. Okay? In the end, I would say that there are two major sources of my course. Design science research is one important background, and also systems engineering, which is the other background that mostly related to the other values. Okay? So in that sense, you have the overall sense of the course. And of course, some examples are through the different bullet points, but I took two exemplary cases also in the end, just to make a graph. Okay? Of course, feel free to interrupt me. I'm not activating directly a part-time moment in the lecture. I would like to go through first the full bullet point and activate the discussion. But if you want, of course, okay. Also, in the remote connection, you can also use your microphone open as you want, because it's easier to me to detect the request. Of course, chat, you can see the chat. So we see that I start from this major consideration, system thinking. You see a general statement of system thinking, the ability to see the world as a complex system, which is very abstract. Let me say a little bit more, but still in this abstract layer. The system is made of interconnected components. Each of the components may be influenced for the other because of this interdependence. Okay? This is very abstract, but if you think a lot of systems that we're dealing with are related to this abstract sense. For some reasons. I'll tell you an example. But before that, let me just consider again this abstract level, saying, if you're able to have an ability to see the system as interconnected components that influence each other, you have a kind of holistic sense, holistic perspective of the system. So somehow you are interpreting not the system with respect to a single component, but with respect to the global element, which is the matter of interest, the overall. Of course, you act on single components, you are making some decisions on single components, but in terms of decision making, the overall sense is the system, the complex. Okay? So in the end, let me say, but it's an assumption I'm saying now, if you are able to have a good mindset in terms of system thinking, you may be expected to be able to decide or make some action that are consistent for the system as a whole in the long run. Of course, you should demonstrate this one. It's very high. But what I would presume to have is a precondition. If you're able to understand the system level implications, you are in a good line of thinking to be able to reach high level goals for the system. Okay? It's very abstract, still abstract, but I tell you, it's one of the first examples I have also reported in the end, but I use now just to talk about the next. 2020, I was lucky to be involved in a project that relates to vaccination. 2020, COVID was exactly in the middle, and the vaccines were arriving, but still we had to organize, at least in Lombardy region, the overall vaccination system. That's the problem. So the problem was related to this. I remind you about January, more or less January 2020. At that time, we had the vaccines arriving, but of course with some uncertainty for the supply, because not all were ready, the quantity was not enough. You may remember something about this. In Lombardy region, we were a little bit late in organizing the vaccination systems. There was still a political discussion on how to make it. We started from the bottom layer. Group of people, also from the university. I was one of those from the university. We were two departments. This department of management engineering and the other that relates to construction. And there were other stakeholders with their own competencies from the medical side, from the organization, logistics side, and so on. So this means that we created this table, but in the end, around this table, there was a lot of competencies, some multidisciplinarity, if you want. And this was bringing some understanding to the problem, which is one of the very first points when you're designing something, understand the problem. Okay? And of course, while understanding the problem, you are discussing about goals or objectives to reach. And so it's a discussion that relates, of course, to what you will design later. But now, part of the design activity, was that a complex system? Yes. Why? Just telling you some elements in the scope of work of this system. The healthcare system is translated to some variables. Doctors and nurses, number of doctors and number of nurses relevant. These are managed according to the health system, not necessarily to the specific initiative we needed to develop in the short term. Second, logistics of the vaccines. They were running in Rome, which was, I think, Porto di Mare. It was a period in that place, the centralization there. They were distributed to the regions with some protocols. They should be distributed in different places. So logistics also is a kind of subsystem of the other things. Third, think about where to make vaccines. If you've been vaccinating here in Lombardy, if you have this experience, in the first wave of vaccination, at least that one, you were not entering a hospital. You were entering a facility that was built for other reasons. There was a choice behind it. Not to avoid that regular therapies were in conflict with this vaccination, which was a massive work to be done. One of the initial decisions to solve the problem was to find out places, facilities, where to install vaccination labs. Okay? So in that sense, you may understand that also the facilities that may be around the scope of work was the Lombardy region. Around Lombardy, maybe of different kinds, may be subject of different interests from the local authorities, from the regional one, the local ones, and so on and so forth. And of course, the last one, the client, the one that has to be vaccinated, of course, sees the system as a system that is serving the vaccination, potentially close to hometown, in an adequate time slot, so to be vaccinated in a quick way, but also to avoid, remember, at that time there was the risk of grouping that maybe could propagate the disease and so on. So there was some, of course, consideration in that. So I told you at least 4 elements, 4 components of the system that tells you about the complexity. Logistics, the facility themselves, the healthcare system, doctors and nurses, and the people who run them. Okay? Clear? What is a complex system? And complexity was around, let's say, related to a time horizon which was very short, with some aspect. It's making it more complex what is happening. Okay? So, if you were not able to share around the table the whole competence, the multidisciplinarity that is around there, the different knowledge backgrounds, you could not solve the problem in a short time, so to be ready for the vaccination from January to April. Vaccination started in a good ramp up in April. Then I will tell you a little bit more about the story when I will retake this at the end of the lecture as an example. But this was just to give you the sense of making things that are complex based on multidisciplinary domain and try to define the logic, remember the concept of logic, of the system, which is robust in the end, which works well. You could have a disaster if you were not making a good logic for the Lombardy region, 6 million of persons to be vaccinated. If you're not doing a good logic, it's a disaster. Yeah? So that's a very good sense, I think, I hope, gives you the sense of complexity. And it motivates the fact that you need some capability to be system thinker. And so to think about the different components in the system and think the implications of the relationship of components for the overall system level performance. Okay? And of course, this requires some mindset, this requires some experience. I'm telling you also you, with this lecture, I do not believe you are going to appreciate system thinking. You have to experience it. The more you experience system thinking, you will discover that this helps you to have a look at the system, which gives you an ability to think about the implication across components to have the emergent behavior at the system. Okay? Is that the case for other contexts? Yes. To me, in my experience, I have rail infrastructure, for example, but also manufacturing system. Even in a small scale, when I'm changing from, let me say, traditional robots that are bounded by some protection with no people around them, when I move to cobots, collaborative workplaces, where I have a collaborative robot that works with a human, of course, you are introducing some complexity. Because you have heterogeneity. The robot is not the human is not the robot. So the requirements that relate to this system are, let's say, different. And in a large sense, I would say that it's more complex than the traditional. Do you have a sense of this complexity? Can you feel the fact that, of course, I'm saying something which is obvious, of course, the cobot should be worked in a safe way and should be equipped with some elements that enable it to work in a safe way, not to create some problems to the humans, safe operations. By definition, we're working in the same working environment, so this is a clear problem to be solved. And so the designing of the cobot should have some characteristics that enable to cope with this safe operation. I'm not saying that we are not safe with the traditional robot, but there is a kind of say separation of problems. The humans will not enter when the robot is moving. Of course, if it enters, of course, it's totally unsafe. Obviously. Okay? But just to say that in the same workplace, we are placing together two different kinds of resources, two different components, makes the problem more complex by definition. Another example is about this relates to another kind of research. Remember that I'm sorry, but I'm an industrial engineer, so I have some examples that relates to my experience. This example is a little bit larger with respect to a single factory because it relates to product that may be seen not only as a product but more as a product service system. I'm not discussing one SpaceX or Rolls-Royce, or the other one is more on chip service, our product service system. I would like just to relate a little bit to theory of PSS, product service system, for those who does not know them. Let me say that in the end, it's important, the product, but it's more important the infrastructure through which you are delivering service. You need a control room, you need some sensors on the product that enables to monitor from the control room. You need some people prepared for field service around the globe, if this is a global action, and so on and so forth. So you understand that there is a kind of infrastructure that delivers service to be built, and which is part of some, say, consideration of system thinking and complexity in the system. Okay? So another example. To conclude this initial part, because my objective was just to think about the complexity we may have. I have a third example, but first let me give the definition that are written there, but let me comment a little bit upon that. Let me say that there are, say, in general sense, two kinds of complexity. One is more technical complexity, and I will define it as structural and behavioral. And the other is more, say, social political complexity, social technical complexity, related more to, say, the social perspective, the political perspective of the system. This is also complex. Structural and behavior is the most technical part. And in the end, it depends on the way the system is organized, the way the system is arranged in terms of organizational networks. The organization may include many components, different types, diversity of components, so some heterogeneity is there. Different kind of relationship which are coupling the work of components or decoupling the work. Coupling in the sense that one very much depends on the other. Decoupling, there is some way to say, make a little bit independent. Okay? It's quite abstract, but in complex systems, you may find this kind of elements that can be intended as attributes to describe the complexity in terms of organizational, intrinsic organizational systems. These are, say, very limited, but in an abstract sense, but in the end, you can recognize some objective attributes to give a sense of complexity, okay, in terms of organization. Your research, Maya, I know your research. I think it has some organizational complexity, right?
Yeah, absolutely.
Can you elaborate a little bit? I'm not fully sure that you can be listened from people in the. Can you talk just to check if it's you can be listened or not?
Yeah. Hello there. Can you hear me?
I don't think so.
No.
Yes, we can hear.
If you are able to make this exchange,
Yeah. So, can you hear me now?
will be good. Yes.
Almost easy. Yeah.
cannot be there. This is complex. Can you hear me now?
Yes.
Okay, I will leave the talk to Maya, one of the tenants here. He will tell you something. Tell me if earlier or not there.
Yeah, so I looked at Maya and one search business for power to XT systems, which basically means it's about how to convert renewable electricity or energy and then later on renewable chemicals or such. And I think those are quite working capital management to be precise, so it's not very technical.
Grazie.
Side of it is
Vedi poi la porta che...
and then the one.
Anzi,
And yeah, there are a lot of stakeholders.
se dici in inglese...
The weather is one variable there that's adding the complexity logistics of the strategies as well, having to store hydrogen and the others. So yeah, there are many different parts.
So there are different diversities there, right?
Yeah, absolutely, and they are location specific as well. So the ecosystem is not the same in Iran.
Okay. It's not so efficient in the stage.
Okay, now my hair is there. There you go.
Thank you. We will try next time. Can you hear me now? Again?
Yes.
Okay. So, in general, the complexity in terms of structural complexity is, let's say, a base ground for one other important complexity which relates to the behavior over time. So, of course, if you are having, say, components that are interdependent between them, they have some relationship that is established, let me say, the kind of static property. Of course, I'm the owner of some asset. I'm the investor on other assets, I'm not the owner. Maybe I'm investing some money, working capital. I am the operator of some asset, but I'm not the owner. Somehow, I'm not telling you in this case, but others. So this is more related to the relationship, the static structure. But in the end, when you see the system living during its dynamics, the complexity may emerge also from this side. It's important to understand the behavior of the system, and this is not that easy because it may depend on some, of course, the time is an important variable, but let me say also on the state of the different components, depending on the state, there are some dependencies on the way the system will work. If one component is in one given state, you may have a course of action that results from this state, and so there is a behavior. If you have another state, depending on this condition of another state, you may have other courses of action. So you may be able to understand that what is inside the structure, which is complex, is an organizational matter. But when we look at the dynamics, so dynamics to me is equivalent to behavior, the interaction of the components over time, their own state, interdependencies, brings to the behavior of the system, which is not easily predictable, especially when you have complexes. So for this reason, you need some capability to study the behavior of the system as an emergent property on the behavior of the system. Okay? So this is basically the technical complexity. What is more related to, let's say, the characteristic of the system in itself. Maya was mentioning also stakeholders. Stakeholders may be seen as part of the system, yes, so they are part of the organizational structure, but may be interpreted also as interested parties, they may be interpreted as interested parties over a system. So you are like an observer that sees the system according to a specific perception. The stakeholders have not the same perception by definition. Because each stakeholder, if you think about each stakeholder, I know that you probably relate to some work, right? Maybe later we will see. But multiple stakeholder perspective is an important matter when you talk about complexity. Why? Let's start in a generic sense. Of course, each stakeholder may have its own interesting perspective, its interests. It has some professional background, some experience, some roles in an organization. Some, let's say, there are some background that are influenced for a perception of the system. Okay? Somehow there is subjectivity, subjective perception. A stakeholder has a subjective perception of the system. Is that not valid? Is it valid? It is valid. It's part of the problem. When you're designing a system which is complex, you may expect more stakeholders with different perspectives. Subjective ones, but influence for the decision. No? Think about my case of the vaccination system. Imagine people from healthcare system were bringing a lot of knowledge that was a gap for me, but were bringing also their own interest or perspective. The same happened for others, the same happened for me, of course. But I'm saying this because in the very beginning, it was curious that we're saying that, no, there should be one doctor and one nurse. How they are saying this? What is the basis of this discussion? One doctor and one nurse. So if I was accepting this, it could say, okay, we simplify, we take this as a rule, it's good. If I would like to discuss this, I should try to convince that stakeholder that it is not one-to-one. I will be back on this later. It's part of the example. But it's just to say that around the table, you may have a mix between what I talked about technical complexity of the system and what is social-political complexity, which is a subjective perception, but in the end, it is influenced for the development of the system. Okay? So this is the general definition of complexity. I'm taking an example from a case that contextualized in infrastructure. This example comes from a PhD work that was developed by Boris Petreni. He was working with Professor Tur. I had the pleasure to discuss with him when he was here just in the postdoc period. Probably I was meeting him, of course, during the PhD career, but I had more discussion after the PhD end. So this is a kind of interpretation as exemplary case, just to synthesize what we already discussed. The complexity, in terms of the infrastructure themselves, of course, if you think about the sole infrastructure, the railway, the electric distribution, and so on, of course, they are physical elements, but you may think also about a mix with the social system, with the management system first. And of course, you understand that the natural systems are important for the infrastructure because you're having a snowfall. This is impacting somehow the infrastructure, more or less. Okay, so the idea of the thesis, just in a rough sense, was to, let's say, study the role of information sharing and collaboration between infrastructures, more than one. So to have some resilience with respect to big events. Think about the snowfall as an example. So somehow, of course, you may see this as a complex system, think from a technical point of view. Without any comment, but this structure is showing in a graph a number of nodes, which are the infrastructure themselves, a number of arcs, which are the flows which determines the relationship between the infrastructure. Is a structural understanding. The flows are just seen as one infrastructure is providing, let me say, some information from another, some energy from the other, some material from another. So from one to another. Okay? Of course, it's also a model. Yeah, it's a model. This is telling you some structural understanding of the system. But due to this, you may understand that time variable is important. So the interdependencies happens over time. So for this reason, I would say that we move from the structural perspective to the behavioral perspective. This is very abstract. It is telling you in this diagram that there are some transitions that related to elements in the system, which may be in killer state. This transition may happen or not, depending on the state of the system. So there is some state dependency there, and this determines some behavior. Okay? So imagine that we want to study how the overall system of infrastructures is resilient to a big snowfall. That's the problem. And how information sharing may help to reduce a little bit the impact of the snowfall. That could be a question. I don't know if I don't remember if it was the real question, research question, but it is related to the problem. Okay? So when you think about this, you understand that there is a technical complexity, but you may understand also that when you think about the stakeholders interested in terms of the system you're going to develop, the info sharing, the stakeholders are many with different perspectives. And the citizens, of course, the first stakeholder as a user or customer of a service that is provided by the infrastructure, but also the operator of each infrastructure are stakeholders. Also, the regional authority is a stakeholder. If you think about the three stakeholders, they do not have the same objective. Or they do not feel that there is a problem in the same way. Problems and objectives are kind of two sides of the coin. On one end of the problems, on the other end of the objectives. So this is the two perspectives you may have in the discussion. Okay, so for example, you may know we're citizens, and of course, first of all, we're thinking about the services, the delay of service. So this is for sure for us important. But maybe for the infrastructure operator is more the capability to allocate resources, the decision support you may have. The regional authority, of course, takes care about the domino effect. I do not want to go into the newspapers, just to be provocative. But you understand, of course, it's economic loss. We may think about different stakeholders with different objectives. Okay? Or, let's say, again, with different feeling of the problem. One problem is more important than another. Okay? So this is to think about the fact that in the overall discussion, I'm just opening this, we may think to start from the target stakeholders which are relevant to manage the socio-political complexity. And somehow in the discussion, you may try to, let's say, synthesize the problems of interest of this stakeholder. So somehow it's a collection of problems with some prioritization, whatever, but it's just to understand what are the drivers of my engineering activities. Because in the end, remember, but I will be more precise later, that I'm approaching design activity because I want to make a problem solving. Okay? So the problems that are more important or less important are very important in the end to drive the design activity. Okay? So it's clear that if it relates to a social political consideration, and it is related to this most of the time, almost all the time, understanding the problem is very much important to motivate your design activity. That's it. So for this reason, I believe that stakeholders are one of the first starting points to discuss the design activity. Discuss with them, have a conversation with them to find the gaps in their own perspective in terms of, I see a problem. I see a problem, so this is a gap to fulfill with some solution. You want to reduce the problem. Or let me say in other ways, which is another sense of a problem. I see an opportunity. Sometimes the problem is not well understood, but you can see that there is an opportunity to fulfill because it's not expressed. Yeah. Okay? I think that these are quite general. It's common sense. I'm not building so much on the theoretical consideration. Of course, there is some theories that relates to system engineering, to design science, but it's common sense. Okay? So it's important, I would say, just to conclude this part, that we deal with the complexity. We may have a different perspective of complexity. When we're dealing with the technical complexity, of course, we will have some methods that enable us to clarify, understand, analyze, act upon the complex system in terms of its structure and behavior. When I'm dealing with a social political consideration, there is the other side. We say I have to create a kind of conversation, I have to collect some issues that are the major concern of different stakeholders, and so engage stakeholders in my research. Okay? The overall things, then, of course, not necessarily is sequential. You may start from one point or the other. It depends sometimes on the circumstances, on the opportunities of your research, on some constraint in terms of time, resource in general. So maybe sometimes you start from stakeholders, sometimes you start from the understanding of the technical problem of the system and back to the stakeholders. It depends. So this is just a consideration that I would like to share in this first part of the lecture before entering into the design science research, which helps me to introduce a paradigm, let's say, to think about this design. Luis Felipe, do you want to make some consideration of the stakeholders' perspective of your research?
On the research, yes.
Just let me review this one.
So that one or the...
Or you can come here.
No, maybe
it's better. Check if they can hear you. I will switch off.
Can you hear me? Hello, hello.
Yes,
Hello?
we can hear you.
Okay, great. So I think that in this part for stakeholders, it is important in my research work as they have an important role since somehow the research needs to fit their needs. So I'm developing sort of a methodology for the implementation of digital twins in the industry, manufacturing industry. And I've been working like in the joint research with this company that always like seeks a certain goal. So I need to match their needs with also the needs from the same like perspective. I think this is quite complex, but also to have in mind that certain company also has different clients with different types of sizes, company sizes, different perspectives, etc. So when you open that scope, it gets even more complex. My thoughts.
So basically, I will switch over. I don't know if they were hearing you because it was like, I don't know. Could you hear the consideration from Luis Felipe or not?
Yes, I heard.
Okay. Okay, so this first part was just to share with you some theory that comes from my major source was system engineering, applications in system engineering. But in the end, it was also to make a forward the background for the next discussion. I would like to talk about a little bit design activity. Here I'm relying on some publication that I mentioned through the presentation. One of the important milestone in design science research is the sciences of the artificial from Herbert Simon, which is, of course, related to some consideration I was already doing, like say, complexity, but also one very important fact that is whenever we are talking about some, let's say, some system, any kind of system, we will see later some classification, it's man-made. It's created by man, Leonardo. It's created by man is something which is, on the word of Herbert Simon, is artificial. In the sense that it's not coming from natural system. And when you're creating this, of course, there are some elements that brings you toward the goal. You develop artifacts, artifactual solutions, systems that are designed using some equivalent terms, so to achieve some goals. So in this statement, in the end, there is the kind of research we're doing. It's a problem-oriented research. The goal relates to resolving problems. So that's what is driving, I told you already in the beginning, just protecting a little bit the discussion. We know that problems depends on the understanding of the stakeholders, but problems are also the driver of design. So it's important to have in mind which are the problems that enable us to make a good design. Just a brief story. In a large sense, engineering disciplines are building new artifacts. Who is mechanical engineering? Do you agree? What do you think? I'm saying mechanical engineer just to open a little bit of discussion to others. What you're building as a mechanical engineer?
Yeah,
As you want, make it exact.
machines.
Someone has to talk about this. Want to talk about this? Machines. Let's take a historical perspective of machines. Why do we build the steam machine? There was some reasons. First, last revolution. So there are always a reason. Yeah, there's problems of goals we want to achieve. And of course, I would say that in general sense, I would make some examples more from the industrial engineering side. Industrial engineer. When people in the Toyota production system were developing the framework of methods, they had in mind for sure problems to be done. Is that clear? I think it's clear. And I would say to be provocative, I'm not a scholar, I'm a practitioner. The Toyota production system is making basic research. We are doing design of new things. No? Just to provoke a little bit. It's not the theory of lean manufacturing. It's the design of a new system. The one that later will be called lean manufacturing. Here. No? I'm telling you a specific case that relates also to Toyota production, lean manufacturing. When you're discussing about cellular manufacturing, buildings, manufacturing cells, there is a lot of discussion of people that invented the methods to develop cells. Professor Barbich is one professor that has an award in a community I'm normally involved with. And the most of his research relates to some methods based on the production flow analysis that were developed to solve problems in practice for building cells. So when we're in this perspective, we are engineering new systems. Activity-based costing, well known, but some has to be developed at this. Robert Kaplan was introducing this to what he called action innovation research, which is not far from design science. You're building activity-based costing, evaluating these in different contexts, so to be able to prove the validity of the new solution. Now we see this activity-based costing. Okay, we can apply there, there, and there. No? But some has to be invented. Design. So engineering is very much related to this design. Designing new systems, proving new systems, evaluating new systems. There are some, of course, drawbacks in this, but I want just to remark a little bit the perspective we're taking. Okay? So, in this historical perspective, I would say that the book I mentioned by Herbert Simon is considered for sure a reference in the discussion, the research discussion. So you see this say, quite recent in the last edition. In the end, it's 20 years, more or less than 20 years. More. Some discussion is in specific disciplines. I would say that I've been reading good papers that discuss about using design science research for the operation of math. At large, of course. So it includes consideration of industrial engineering, it includes consideration from the management of the operations and so on. It is a discussion that I can find in some papers that is good, informative, linked to some topics that, of course, are of interest for management engineering. Okay, so what I would like to remark in this that, of course, when you're designing a new system, in the end, it's nothing new. But also, say, the paradigm that you may follow somehow may depend on the context where you are. You're an engineering of a software, you're an engineering of an industrial system, paradigms are not exactly the same. However, they have some commonality. So this commonality will be shared with you now, taking some consideration on the principles, and then on what I call the nominal process to follow. That could be, say, informing you in some action, design action. Okay? So this is, first of all, what I would like to remark in the next part of the lecture. First, I already introduced this consideration, but I would like to remark again, maybe using the operations management as a target field. We are driven by the interest to develop solutions in front of problems, all opportunities. This is what is the interest of a research, of a design scientist. Okay? It's quite, I suppose, a clear statement, because in the end, design is an act of creation of a solution, the designed solution, with response. That's the major interest we are having when you're taking this design scientist perspective. Note that it's interesting to say that, of course, if you take this perspective, it's somehow, by definition, related to the engagement also with practitioners. People in industry have real life problems. Maybe not well-defined opportunities, but saying that we're following design science research, apart the scientific rigor, it's a way also to bridge with practice. It's a way, not the only. But it's true. So in the end, apart from being a methodology, you may think that when we're doing design science, we're having a strategy, creating new solutions and evaluating new solutions, thinking that we can make errors, violent errors. So in the end, you are having an explorative strategy. You are exploring. You are building a solution. You are exploring if it works well. What is not working well, you try to say to correct, amend some part, and develop further. So let me say that the research strategy behind design science is explorative one. You are exploring. You need, of course, context where to explore. Think about, again, my case of Toyota production system. Think a specific problem of the overall concept development behind this Toyota production system. Think about the very specific problem of setup times. By the way, let me say, of course, the problem could be stated as long setup times. That was the problem at the time. It is, at the end, it's more a symptom than the problem. It's long setup times. But it's symptomatic of a problem. That is problem real. Long setup times. Now, the point of, let's say, being driven by the problems, we'll have also an example for opportunities, but let's start from problems, long setup times. Being driven by the problem is not a problem of identifying the problem. If you go back a number of decades and you enter in the Toyota production system, you could find a problem. You can understand maybe with not clear identification of the problems, but the problems are many. It's a matter of framing them and understanding them, rather than identifying them. You enter into the production system, you could see that some problems are more important than others. There is a discussion between different stakeholders. Remember the socio-political consideration. And in this, there are some potentially multiple domains of knowledge at the background. And enter some decades ago into the Toyota production system, understanding the problem, think about the long setup time, was in relationship to the technical activities related to the production equipment, preparing the mechanical equipment. I was asking a mechanical person because I was making some consideration in the background discipline. The long setup time is a problem that relates to the technical activities of this production equipment. What means? Identify the symptom of the problem, long setup times, that were relating to some possible reason. The technical specifications, activities are related to the production. This is not yet a solution, but it's a way to understand the problem. Can you follow this? You have just like going beyond the symptom and understand what is the cause of the problem. This is helpful for me because I'm dealing with maintenance management, asset management, which deals a lot with diagnostics. But in the end, if you think about a designer, is thinking about the problems and thinking about the root causes where to come to improve. Okay? It is a simple example to say, this is historical, this is, I think, well known, at least in the general discussion. But on one end is to remark that real life problems are there. You have to understand, you have to frame them into some consideration. Second, of course, framing and understanding the problems may be influenced by the context, by the stakeholders, and so there are some different factors that are playing the game there. So, some decades ago, we could arrive to this kind of understanding of the problem. Of course, if you move today, it could be not only this understanding, it could be farther ago. I'm thinking about one paper that I saw that related these long setup times, not anymore to production activity, but more to information that is mentioned, which is design of information. But to do good setup, you need also information. So somehow, the framing of the problem, the understanding of the problem has changed because of the context. It was not anymore Toyota production system. It was a printed circuit board assembly system, semiconductor one. So maybe the context is relevant to see this problem. Also, the technologies today, you do not have problems in the production given. You have problems in the information management. You have already solved some problems. Are you encountering other problems? No? So I'm seeing these two examples, compare these some decades ago, long setup times due to the production equipment and its technical, let's say, activities that are there. Understanding that comes from a discipline which is mostly mechanical engineering, industrial engineering, close to mechanics. Today, in another context, recently, long setup times probably are not anymore there. And also, it's a matter of improving further to decrease the setup time. Now, the discipline is not mechanical engineering, it's information engineering. That is behind that understanding. Can you follow this? So, this to say that the discussion of problems is not about only identifying, but you may have many. Of course, you try to prioritize those that are more important. But it's more important to understand the problem so to have a kind of link to a possible solution. Back to the solution now, in my discussion. If you think about the production equipment and the problem some decades ago, the solution was, let me say, in general, to make a simplification of the process, technical process, and to adopt some ways to make these simplifications. There is a methodology, there is a method that is known on the framework of these methods, which is single mills, SMEL, single mills of exchange of dies. There are some practices that have been captured in this method, single mills of exchange of dies, that could be applicable where to simplify the process and make it shorter in terms of setup time. Someone had to invent this SMEL. Among other methods. If we move today, the problem has been framed and understood in a different way. The example of the PCB assembly system. We're not acting as a solution on the methodology of the past. We're adding some other methodology that may be related to wireless connection, relational databases, and so on. So more from the information side. Yeah. So it's important then to be, say, on time on the problems. Be in the real life. Be related to the current problems we are living in. I believe that industrial world has a lot of real life problems to be. So in some way, I would say that when you capture problems, you depend on the context, you depend on the stakeholders. As a researcher, you may habilitate a way to find a problem that is somehow problem. We're not a consultant, we're a researcher. Okay? So in that sense, the robust way to find problems or opportunities may be based on some ways of doing things. I would later discuss a little bit the scheme, which is the concrete element I would bring into this lecture. So this schema is basically telling you a number of steps to go through as a process to make design science research. I'm making some comment later. I would like just to reflect a little bit on some elements that I already remarked a little bit, but let's work in comparison. Design science, we already discussed. It's has its own roots in engineering, has some kind of interest in problem solving. So this is the main driver of the design science. As I'm a design scientist, on the most part of the time, I've been always looking for problems in industry, because my interest is in industrial application. So this was clearly discussed until now. I would like to remark a little bit more the exploratory nature of the research. When we think about solutions to a problem, we may admit that we can make errors. We need in the cycle some evaluation to identify some pitfalls, some problems that are still inside the solution. So somehow there is an iterative process by definition, which leads us to explore different versions of the solution. Correcting some problems, reducing, mitigating the impact of those problems, improving in the end the design solution. So in that sense, fundamentally, we start from the creation of something. We need to observe this that was created, so to evaluate if the solution is working well or not, and redesign. So this is a typical iteration you may have from time to time in this kind of research. Quite obvious to say, but it's also to remark the paradigm. The paradigmatic approach is starting from a moment when we do not know exactly the solution. We are having an incubation of the solution. But for sure, it's a rudiment. It's something which is draft, not yet well defined in the details. So going through the iterations, we are establishing a better understanding of the solution. Also thanks to some evaluation in some specific context. So the feedback we're having from the evaluation is a feedback helps us to understand better and evaluate, of course, and then improve the design solution. So it's part of the work in the end. We should admit that, because this helps us to improve our design solution. There is a comparison that is proposed by this very good paper, Olmston. It's from, now it's Aalto University, before he was doing his PhD in Helsinki University Technology. It's from Europe.
Yeah, cool. Yeah.
Young Olmston. I think it's a good paper, but it brings a lot of sense in this comparison. I will not go into lots of details because my objective is to understand design science with respect to other fields. He's providing you more details so to make this comparison if you want to deep dive into this discussion. But it's important to me to think about this comparison between exploratory research or explanatory research. I tell you that one of the cases, exemplary cases I was already mentioning. Professor Barbich was developing some methods based on production flow analysis to help design manufacturing cells. So he was contributing with some inventive system, to help in cellular manufacturing. I may imagine, I was not living with Professor Barbich, but I may imagine how many trials he has done in different ways. And he was inventing a new method among others that can be found in the literature. So this is an important contribution on the production flow analysis method. Okay. I would say that he was exploring, so exploratory research. I would remark one method that is also important here. The phenomenon that he wanted to study was not there yet to create the evaluate this. This is a very important feature of design science. So as a research approach that orients to problems. You have to create the phenomenon, method, solution, whatever, before studying this, before evaluation. This is essential, the creation. You cannot evaluate this if you do not have, because you have to bring this global solution to be evaluated. So, thinking about the case of Barbich, he was developing for sure, with exploratory research, the methods he was publishing, trying, verifying, validating them in some context. On the other side, explanatory, think about the same case. The phenomenon is already there. We have plenty of knowledge about cellular manufacturing. We can study cellular manufacturing in different applications, for example, applicability. We're having a large sense of cellular manufacturing in terms of application context where this could be adopted. So, an interest from this side could be, for example, identifying the factors that are most influent for the success of the cellular manufacturing. The question could be, which context is good for applying the cellular sub-question, which are the factors that are mostly influent for success? Cellular. To do this, you have to build some hypotheses. You have to prove this hypothesis. So to have some kind of statistical proof of the fact that these factors and not others are influenced for the cellular manufacturing activity. Can you follow this? So what is the point of this other kind of research? We want to develop, the goal is understanding the phenomenon that existed there, cellular manufacturing is existed there, with a number of methods that are published, with a number of applications that are discussed. I want to understand more about this phenomenon, explaining this in terms of some theories that could be built, if it's not there, could be tested if we have some hypothesis. So this is more explanatory. Both the two approaches are, of course, useful for research. But let me also remark the perspective I want to take here. I cannot explain if I do not have the phenomenon. Also, for explanatory research, I do need that one Toyota production system started. If it started, it created some new system that could be studied later on. One Professor Barbich that developed some methods for cellular manufacturing. So in that sense, we explored, we tried to evaluate some new systems. Let me remark also, we are not able to generalize. When you're exploring, you're having limits in the assumptions context where you are playing the game. So generalization is far from the exploratory research. You need another perspective. But to explain, based on theories, you need exploratory research to create things. Like Leonardo, like Barbich, like people as a collective knowledge in the Toyota production system. So that's the perspective I'm taking. And based on this, I would discuss in this last part some other elements of this approach. But let me check. You want to make a break? Is that okay?
Break.
From the remote connection, is okay?
Yes, on my side.
Any questions?
Yes, it's okay.
Comments? So we can make 20 minutes. Now it's 40, 39. 20 minutes of break and we can start at 3 o'clock. Okay?
Okay, thank you.
Good.
Okay.